All right, can people hear me?
Yes.
All right, great. And can you see, basically it's our lab-ish on the video? Okay, I'm assuming somebody can see my screen because I got a comment in the chat. You guys can see like a protractor and a little beam and all of that with my screen sharing?
Yes.
Okay,
Yes.
great. All right, well, it's 6:59. We will go ahead and get started. I've been thinking of trying to give you guys just a little basic something to work with for the lab, but maybe we will do as usual and start with student questions. And if we need to launch into that whole explanation of how the optics works, we will do that. As a reminder, always make sure to make a comment in the chat for the questions that you want participation in. And I'll have a record of that after the chat is over, and we'll be able to put it into the grade book. All right, so anyone who wants to start us off, feel free to make a comment.
I actually have a question. I kind of joined late. I just joined in. I don't know, is this what our protractor is supposed to look like? Because it doesn't look like anything that the lab was doing.
Yeah, so if you started the lab, you might recognize this because this is what it loads on. You see down here at the bottom, you guys can see my mouse, right?
Oh, okay, it's on intro, not Prism.
Yes.
Okay.
So this is not what your actual lab looks like, but there's a reason why this is the intro. So if we need to start kind of defining how you measure your angles and stuff, it will probably be easier to start here. And then I can also click over. I've tried to kind of get it basically set up in the Prism section as well. But yes, correct, as pointed out, this right here that we're looking at is not what your lab setup looks like. But this is an intro screen within that same simulation that we can use to talk about some of our definitions. Did anyone have a question that they wanted to start with? Or if you want, I can just start kind of describing some concepts that might be helpful. Okay, so people are talking about the clockwise versus counterclockwise. And I will show you, like, that's a reasonable concern. I'll show you what it looks like here. And then we will go over and look in the lab, which is a little bit more complicated. So you guys can see my mouse, right?
Yes.
So this is kind of the basic theoretical setup that we always have when we, if I was lecturing you and we were using the board. And you see alignment's really important. So I'm trying to make sure that I get my 0 right on this dotted line and get my 90 right lined up with the edge of the surface. And if I do that, then I will be able to get good data. And the real world alignment is very, like, that's the biggest, trickiest part of setting up an optics lab like this. So in this, oh gee, can you guys, all right. Sorry, my monitor is going off and on. I don't know if you guys can continue to see that or if it went black for a second, but I couldn't see it. So this dotted line is called the normal. It exists, it's an imaginary line, but it's defined as being perpendicular to this surface. So this big purple thing that you can see, this is as if like we have this big, giant, infinite glass surface or whatever material we want to make it out of. And we're seeing a cross section of it, like it's cut. So we can see this is a little laser pointer and the light is coming down and is hitting the surface. This is the interface is what we call it. So this is air in the room. We can change that. This is glass. And the protractor needs to be right here lined up perfectly at this point where the beam goes in. So our angle defined is this angle that starts at 0 at the normal and is measured to where the beam is. So this is kind of an odd point right now, but like that would be 35 degrees. And how much did you guys talk about this in your lecture? You should have had some background and kind of understood how this works. Is that something you're kind of familiar with? Does anybody like feel like they've seen this before, or do I kind of need to get down into the nitty-gritty and defining it? Everyone's muted, so I'm not hearing any feedback at all.
It would be helpful.
Okay, so we have refraction going on. The definition of refraction is what? It's bending. So what the beam does as it goes from one material into the other, this is refraction. This up here, what is this? This is reflection. So if you have a mirror going on, that's doing reflection. That's an English word, we're familiar with it. So this pale beam up here is reflection. There's always going to be a little bit of light reflected. Like if you have a window, if you look at it at the right angle, you'll be able to see glare. So there's always a little bit of reflection, which is what this is representing. So if I wanted, as this lab, we have to take data at a whole bunch of angles, right? So they say, hey, we need to know 30 degrees. I would put my beam going in at 30, then I would come down and I would measure from this normal down here. So from this normal up here, this angle right here, we would make the little angle mark right here if we were representing where we were measuring. That's an angle of exactly 30 degrees. The angle we're measuring coming out is this one right here between the 0 and whatever this is. So this is 5, 10, 15, 20 down here. And so that would be our data point. Now, if we were going to measure, so this, if we're going from 0 to 30, that's going counterclockwise. If we wanted to measure going clockwise, we would come over here, and it's not going to let us. Just the way this is set up, it can only be over here. But we would come over here and we would put our laser pointer going in at 30 on this side. So it would still be going in at exactly the same angle. And where would it come out? If it was coming in on this 30, it would come into this point, it would bend exactly the same amount, and it would come out at this 20 over here. So you guys see how ideally we would get the same result, even though it's going in at a different angle. Kind of, I mean, it's still going in at 30, but it's going in at 30 clockwise instead of 30 counterclockwise. And so it will still come out at exactly the same numerical angle, but in the real world, if we were taking this data, some of these would be negative. But because we're going to average them, we're not going to worry about negatives anyway. So the 20 on this side would be right here, the 20 on this side would be right here, and that's where our beam would come out if we were able to move our laser pointer all the way around and send it in at this 30 degrees. Does that make sense? So physically, and your lab starts out, everyone, I do recommend that you make sure to read, a lot of people don't read this background information. And that makes it harder for everyone to understand what they're trying to measure, which is one of the big challenges with this lab. So the incident ray is what we call the ray coming in. You can see your theta 1 is labeled here. This is Greek letter theta, represents angle by default. Usually if you see theta anywhere, it's talking about an angle. This is your reflected ray, which is the pale one that we saw coming off. And this is your refracted ray, the thing that's coming out after it goes through the interface. So you can see how this in your lab matches up with this intro screen, right? Does that make sense to everyone? And there's like a whole page of background information. I strongly recommend everyone actually read that. Okay, so our actual lab. And people might say, well, hey, we have this going on the intro page. It's actually fairly simple. Why are we going to go with all of this? And the answer is this theoretical thing where we have a nice, huge infinite T, and we could look at it from the side at a cross section. That's great for whiteboards and lectures, but it doesn't actually exist anywhere in the real world. So this that we're doing with the prism is actually a simulation of a setup that you would actually see in an actual lab, because there's a whole bunch of issues that we have to address if we're going to measure these optics. without our alignment. And we actually have to have a physical piece of glass that we can, adjust and move and measure. And the bigger the chunk of glass, the more expensive it is. And normally to have them perfectly flat and perfectly straight and with measurements, we need to know they're actually precision optics and they can be kind of expensive. So there's no way we're going to get an infinite piece of glass in the lab. So in the real lab, we actually would literally have a little teeny tiny prism like this, and we would actually have a physical little mount that it's on. That you would very carefully line it up just like this. Now, because of this, the normal is still this dotted line, so we know where our 0 is. But when we start moving things, because our light source is fixed, which it kind of would be in the real world, it would be really kind of hard to set up a big optical contraption that would move the laser pointer around the room to come in at different angles, right? So our light source, whether it's a laser pointer or oftentimes it's a little beam of light, it would look more like this. That is an object that's just set up in the lab, and you can't really move it because the alignment would immediately go awry and you wouldn't be able to get any data. So this is what it actually looks like in the lab. You do the lab in the dark and you have a regular little light beam. And so you have to set up your prism and the piece of measuring equipment that your prism is on, you have to have them all set up and aligned. We're going to change it back to light because that's just a little easier. So what we're actually doing, though this is like the whole setup in the lab is rotatable, so you can actually move the 0 along with your prism, which does help. But what we're doing in this simulation is, instead of moving the light beam, which would be kind of impossible to do in the real world, we're moving the prism itself. And that, if you look at this, we're measuring between this dotted line, which is our normal, and where the light beam is going in. So that's actually the same measurement that's being made. We're just making it from the other end. So it's like using a ruler instead of putting, like, say you're going to measure a pencil. If you put the eraser of the pencil at the 0 and measure till the end of the tip of the pencil, you get a number, right? But you could also flip the pencil around or measure from the other end. Start at the tip of the pencil and just adjust it so the 0's at the head of the pencil and then rate it that way. So that's kind of how this works. So we have our beam of light is going in exactly on the 0, and the normal is actually the thing we're looking at the measurements of. So I think that they tell you to move it to 10 degrees. You can see that this is the 10 degree right here. And you have to just adjust. Oops. So the protractor itself needs to stay with the 0 on the beam, because the angle that you're measuring is between the beam and the normal. So the 0 either has to be at the beam or it has to be at the normal. It can't be some other place. So once you get it aligned, so everything is straight, meaning the prism is exactly at the 90 and the 90, and you can see how my normal is a little crooked right here. That means my alignment isn't perfect. So just make sure that the normal is right on the beam, set it up really carefully, and then only move the prism with this little handle right here, because that will rotate it without changing the alignment at all. Okay, so you see as it goes around, the normal can go up to about 60, or maybe it just stopped moving. So if you want to send in the beam counterclockwise, you have to come over to here. So you see, if I was going to take data at like 30 degrees, right? So I would say, okay, the angle between my beam and my normal is 30 degrees. And then on this side, I need to measure between where the beam is and the 0. That's the angle that I'm looking for. Actually, wait, I just lied to you. Strike that. Okay, so you're still measuring with respect to the normal. So this is the part where it wants you to subtract. I'm getting a little confused because they're drawing a normal going along the beam as well, but it's this angle in here. And that's why it's asked you to subtract it on the side coming out, is because you still have the normal. It's continuous with a line that you had the normal here. And remember, the definition of normal is 90 degrees. So it's going to always be perpendicular to the edge of the prism. So this is the edge of the prism going this way. This is the normal going that way. So you don't get confused. And then the beam itself is right here. So the angle between these two is the one you're measuring. So if you have to subtract, then you come out here and you look at this, you look at this, you subtract those two numbers, and that's the angle of refraction. Does that make sense? Does anyone have any questions?
Go
ahead.
When I did that, I mean, I was fine, and then as I start going into like 60 degrees, the crystal was going haywire, and I couldn't even keep it to 0. Is that normal?
I'm not quite sure what you mean by that. So once you get all of these components set up, like this needs to be going in straight, this needs to be in one spot. So the only thing that you move to take your data is you grab it by this handle here, which will rotate the prism. If anything goes weird, like if you misalign it, you'll get a whole bunch of extra dotted lines because the beam goes every which way. That means you've got bad alignment.
Okay.
And so you need to go back and make sure that you're actually, like when you start the prism, it says, I think it tells you to, like, you can't even see the notch, but you're supposed to line it up with this little notch right here. So the edge of the prism is exactly at 90 degrees. And this normal is going exactly through 0. And you're going to get some weird stuff going on if you don't have it exactly lined up.
Okay.
I actually had that happen to me where it was like glitching, and it was because I was reading the wrong line. I was measuring where we put our clockwise refractions with the red line, and with the, I can't explain it right. I was reading the red line where the incident should be. Like where if it needed to be 10 degrees of the incident, I was using the red line, not the dotted line.
Oh,
So
I see.
that's where it got really hard for me to spin it, and it was glitching.
Yeah.
You need to use the dotted line for the incident.
Okay.
And then whatever the red line is on should be your refraction, right? Well,
Yeah.
you need to use the equation to find the refraction, but
well, no, for your data, you take 2 data points. So it tells you to make your incident at 10 degrees, and you do that by rotating it. So you are looking at this angle between the dotted line and the red, but do not try to move the laser. It should, once you line it up very carefully on the 0, it needs to stay there. And so it's always going to be coming in at 0. So the angle between the beam and the normal, which is the dotted line, that's always the angle of incidence. So you just make it bigger and bigger and bigger and bigger. You can go all the way up to 90. Well, if you actually go to 90, it starts moving around, but it should not do that until you actually get at 90. It's possible that you're not reading the angle right and you think your 90 is 60. And so when it starts glitching, that's what you're talking about.
Shouldn't we not use 90 because the incident only gets up to 70?
Well, yeah, but the point, if you move it all the way around, like it does start glitching on me when I get to 90. You see how it's jumping around like that?
Yeah, exactly.
That's because I'm all the way to 90, and you shouldn't get there in this lab.
Exactly.
She's right.
So you're using, so what I was doing wrong that made it glitch is I was using the red line as the incident, the angle of incident. So once I got to 60, it started glitching, and I'm not supposed to do that. You're supposed to use the dotted line. And that's where it doesn't glitch.
Okay.
So it's just this angle over here, and it goes up like all the way almost to 90 just fine. And you should only be going up to 70, so that's fine. And then even at these steep angles, so this angle right here, like this would be 70. We're basically at 75 right now, which is farther than you're going to go. And then when you're reading it over here, it's still the line between the dotted line and the red line. So you
Is
take,
that the refraction?
yes, so this is the angle of incidence over here between the red line and the dotted line on this side.
So that's the 70 degree and
Well, this is like
refraction-
75. It's a little bit,
Oh,
the 70 would be right here. And it's
Okay,
a little
okay.
bit past that.
Okay, then the refraction is 10, 20, 30, 39 or 38. Is it true? Is it right?
Yeah, I'm seeing it, like the 39 would be clear over here. This little thing is a 5.
Yeah.
I'm seeing it as a touch under 35, so like a 34,
So
but
that's
that's
so
not
that's
the
the-
angle you're reading. You're actually reading, you're taking this angle over here,
yes,
which
yes.
is 70 and a little bit less than 5, so like 73 minus 34 is the angle from here to here, which is what we're measuring. So you actually need to write down those two numbers and subtract them to get your angle of refraction.
Oh, thank you. Thank you.
Do we round up?
Excuse-
Like if it's in the red line is in between like two numbers, because like I can barely read it and I feel like they are in between two numbers. Do we round it up to the higher number, or do we?
No, so you're using your eyeball and you're getting the best number that you can. And really these ones, like these tick marks, the bigger tick marks are every 5. So yeah, like you might read it and you might get like one off from what your neighbor might read. But when you're in a lab and when you're taking data, you always have like the last significant digit that you're taking, the smallest number is always a judgment on your part, and you do the best that you can. But if you round it up to the nearest 5, you're not going to get any data that's worth having.
Oh, no. I meant like if it's in between, that looks like 34 or 35 and 34. Would I use 35 or would I use 34?
But that's it could be
These little
36 or
tiny hair marks are the 35 and the 34. So this is 30 and this is 35 and it's just a little bit less than 35. So you're going to be lucky if you can get to the nearest one. Like just get to the nearest one that you can read.
So we would
The line itself is like 3 degrees wide, almost like two degrees wide, maybe.
Okay, so I would do it would be 75 minus 34, and that would be
No, like this right here this is 70 and it's not all the way to the 75. I would call that maybe 72. Like it's right here.
okay.
Which this is the 75 and this is the 70, and it's not either of those. It's like right here.
Okay, let's just say it's on a line and it's 75, and let's just say the other one's on 34. We would minus those twos, and that would be the answer for the table. For clockwise, right?
Yeah. So the clockwise is really like this angle right here. So from here, this is actually the counterclockwise, but from this to this, and then when you're doing the other side, you actually come in, and let's do an angle you're actually doing. Like this 60 is 60 part of your data. Oops, sorry. And here we made a mistake that might be easy for you guys to make. We're moving our protractor. Don't move your protractor. So your protractor is always at 0. We need to use this handle over here. Okay, so is 60 one of your data points?
Yes.
Okay, so you would line it up as carefully as you can, pointing straight at the 60. And so this would be your 60 on this side, and then you would read whatever this angle from here to here is on this side. Now to read your other 60, you rotate it all the way around, past the 0 to 60 on the other side. This 60 over here.
So
Does that makes sense? So this is also 60, but it's 60 the other way, like from here to here 60, and instead of from here to here 60.
Okay, are the angles of refraction between clockwise and counterclockwise supposed to be the same? Because some of them are the same for my table, but some of them are different.
Okay, so if you end up with something different, it's a good sign that you're reading it wrong. So
they're supposed to be the same.
Yes. So the N1 sine theta 2 equals N1 sine theta 1 equals N2 sine theta 2. That's Snell's law. And if you're taking your data correctly, that will always be true. And it doesn't matter if you've measured 60 clockwise or 60 counterclockwise. The result, if you're reading it properly, will still always be the same.
That makes sense because I'm literally a point off.
Yeah. So yeah, if it's like within 1 degree, that's within like your reasonable like uncertainty of your data. Like these teeny tiny tick marks are pretty hard to read. And like we said, this fat red line is actually thicker than 1 degree. So if you're just off by 1 degree, that counts. You're within uncertainty. You're good.
Okay, so yeah, so my counterclockwise is usually like 1 degree, like less than what my clockwise was. So that's fine.
If it's always off by the same amount, that may be a sign of alignment problem. But if it's only 1 degree, that's reasonable.
Yeah, because I think it was just so hard to read.
Yeah, and that's reasonable. You know, like our human eyeballs all have limits on them, and this is a little bit tricky. So yeah, if you're within 1 degree, that's perfectly fine.
Yeah, because when I did the graph, I tried to draw my line as straight as I could. It was not straight.
Yeah, I highly recommend, if it tells you to use a straight edge, you need to actually use a straight edge. But the best way to do it,
straight, you can still cut, like, because my line was not, like on my graph was not straight whatsoever. It had bends.
Okay, so, and that's also a matter of degree. Like you have a certain amount of just laboratory uncertainty that's always going to exist. But it shouldn't, be mountainous and hilly. It should look basically straight. Like if someone came and said, what shape is your graph? You'd be like, oh, it's a line.
I mean, it's a line. It's straight. It doesn't have hills, maybe little bumps.
Yeah. So and the other thing is does your lab tell you to take a best fit line? I think it does.
Straight edge.
Okay, yes. So that, like the shape of your graph and a best fit line are 2 different things. So I strongly recommend, like I did earlier, use a spreadsheet program. It literally takes like 30 seconds to do your whole graph in a spreadsheet program. And then you just go into the menu and it says, give me a best fit line, and you click it. And then you say, give me the formula for that best fit line, and that you don't have to calculate your slope or anything. It just prints it right on the graph for you. So that is the strongly recommended way to make your graphs, especially this late in the semester. It's nice to do it once just for the experience, but you guys don't need to be graphing by hand. It's not time effective, and it very, very rarely do I actually see a graph that comes through that gets full credit when you could just have the computer do it for you in 30 seconds. Like it's
so we just use the Excel, Microsoft Excel.
Yeah, you guys all have access to that. I actually kind of prefer Google Sheets, but both of them will do it for you. And it works the same way. Yeah, and some people, so the school provides you access to Microsoft products, but normally they're a premium product that you might not always have access to, depending on whether you invest in that on your own, but Google is free. So you can always have that and always use that for basics like graphing.
I believe the school provided us Excel, but I just didn't know it did graphs. Would I just go to google.com or Google Docs or?
Yeah, well, do you have a Google email address?
Like a Gmail?
Yeah.
Yeah.
So if you do that and you log in and you go to drive.google.com, it will take you to your Google Drive. So if you have any previous documents, they'll be there. If you've never done it before, you can just push create a document, and they're color coded the same way. Green are spreadsheets, blue are like Word documents. And I think it's called Google Sheets. And it looks pretty much the same and has the pretty much same functionality as Excel. The menus are a little bit less elaborate.
Awesome. All right. I appreciate that. Thank you.
I have a question for you. You explained this table so much, but I and Lee, we working as a group, and we got 2 different numbers. Could you please give us the favor and just do one of this degree, like 70? We want to make sure which one is true.
Or I can I read it? So right now, the angle of your screen.
Oh, yeah, sure.
Yeah. And
okay, go ahead.
So is that the clockwise 60?
Yeah, so it's not all the way on 60 now. I think we were doing 60 before, but 60 would be over here. And we, dang, I just
That's
accidentally
the
moved my
clockwise
protractor.
or- okay, that's the clockwise 60.
Yeah, just a second. I was trying to move it and make
Yeah.
sure the alignment was perfect, and it
That's the
moved my
clock,
protractor.
yeah, counterclockwise.
Okay, well, let me, all right. So it's the angle measured, oh,
The counterclockwise 30s.
okay, so, oh, yeah. So really, okay, yeah, so you're measuring from this angle. So technically, sorry, I haven't gotten it all the way to the 60 yet.
Okay.
So
So-
technically, if you're measuring from, I'm not quite sure how they're defining counterclockwise and clockwise. As long as you're consistent all the way through your lab, it's not really a big deal which is which. But if you start from this line and go to here, this would make this the clockwise one, because we're going this way. So
Okay,
this is 60 right here.
Okay, 60. And
Mhm.
the refraction is 10, 20, 34, 35, 34.
35.
Yeah.
Right.
Yeah, it looks pretty close. Yeah.
Okay,
How
so that's
about-
And then, well, that's just one of your numbers. You need to take the other number and then you need to subtract them. So we're reading this and we're
Yes.
also reading this over here.
And you mean
Minus
it counterclockwise is 30 or it's
Well, no, because so this, the angle of incidence is 60.
that's 60, and the
The angle of
refraction.
refraction is the angle between this line and this
And
line, which
yes,
means you have to read this angle of 60 whatever right here, that
Yes.
where this black dotted line would cross the scale. You have to
Yes.
read this angle here that you were calling 34, and you have to subtract them, and that's your angle of refraction.
Yes, got it.
okay. Thank
So
you so
probably-
much.
Okay, great. Anyone, like, is that making sense to everyone? And
Yeah.
then when you go to do the other side, you actually rotate it all the way around here till the black dotted line is pointing at 60 on this side, like that. And then you see how basically these are the same numbers. Like this is right near the 34 or the 35, and this is just a hair past 60 on this side, but they're in a completely different location, but the numbers are the same. So you would take this 60, whatever you want to call it. This one actually looks kind of close right on 60, minus 34, 35, whatever you want to call that. And then this is your angle of refraction on this. So one is counterclockwise, the other one is clockwise. Okay. All right, so the question in the chat, I'm a little confused. When filling in the table, we line the dotted line on the angle of incidence, and our answer we would put into the equation would be lined up with the red ray. So this is just a question about taking the measurement. Do we understand how that is done now? So on the table, you actually just write down the angle of refraction, which is this total angle, this number minus this number. So like make a little note off to the side or just have a scratch piece that you're taking all your detailed data on. And then when you fill in the table, make sure you only just put one number in that box. Does that make sense?
Yeah.
Okay, and then, obviously fill out everything it asks you to fill out, answer all the questions it asks you, but only one of these numbers is the angle of refraction, and it's not any of the numbers that are actually written on the scale. It's the difference between these two. So do the subtraction elsewhere and only put one number in the box. Okay, is that clear for everyone? And then remember, everyone else who asked a question, make sure you put something in the chat so I have a record of it for participation credit, unless you've maxed out already. Okay. Are there any further questions? Any more confusion?
Yes, I just want to make sure, just clarify. So when trying to get the average of the angle, you just add the two angles clockwise and counterclockwise, and then divide them by 2, which it should be the same answer. So if it's like 7 and 7, it'll add to 14, divided by 2, it'll be 7 again.
Yeah, and then if it's like 7 and 8, you'll get 15 and you'll end up with 7.5.
Yes, okay. Just making sure. Thank you.
Yep, no worries. Is everyone else clear on everything that they were hoping to clarify? I hope actually being able to see it on the screen really helps.
For number 2, getting the sign for that, is this a calculator thing? I see everybody's,
Yes.
okay.
Yeah, nobody's like, I know some people were like, oh, opposite and hypotenuse. Yeah, you're just going to enter into the calculator sine of 30. Okay, so also some calculators will have a radian mode. And so all of our measurements are in degrees. So you want to here, and I think I usually post a hint on this. I'm double checking. Okay, so if you get sine of 30 is minus 0.988, that means you're in radian mode and you need to change to degree mode. So if you get sine of 30 equals 0.5 exactly, that means you're in degrees and everything is good. So if you're a little worried about your particular calculator, whether it's in radians, whether it's in degrees, if you guys can see, you guys can still see my screen, right? So on the Google calculator, you see how this box over here, you can switch it back and forth. And I typed in 30 degrees exactly, just so you could make sure you're in degrees. But this rad and this deg, if you click back and forth, you'll change the mode. So just like do your sine of 30 on whatever calculator you're using, make sure you get 0.5, you know you're in degrees. If you get anything else, try to find whichever switch changes the mode. If you really are concerned about it, you can do what I did up here and just do a search and specify degrees. That will also get you in the right mode. Though, depending on what you guys are doing for your other classes, I always strongly recommend, because you are not going to have Google in a test, to have your scientific calculator that's usually required for this class and use it and get familiar and comfortable with a calculator. That will also serve you really well on all your standardized tests, your admissions, different things that you have to do for college elsewhere. But Google will always get you out of your basic math in a pinch, as far as there's actually an integrated calculator right in the browser. Okay, any other questions? All right, well, great. I hope that this is helpful. We will get it processing so we can get the link up. And my apologies to anyone who was here last week and we got the wrong link posted. A couple people mentioned that. Feel free, if there's a technical difficulty like that in the course, you can message me directly. I don't get comments promptly, but I do, like, a technical issue is always appropriate to just, email me or just use a Canvas message. I usually get those really promptly. Any other questions or concerns? I posted an update on the grading situation today that this is going to be our last lab, and grades should be updated on or around May 6th. And then, as I mentioned, we'll make a extra little announcement. Hey, everyone, check your grades. And if there's anything that was missed or whatever, you can message me for about a day before I forward those on to your lecture instructor. Also, we are counting down less than 1 minute on our automatic cancellation. If we want to, we can keep going, but we will be logged out. Is there any other questions? All right. Oh, sorry, is anybody about to say anything? All right, if you guys are good, I am good. I will start. It does take a while to process, but I will try to get the link posted and you guys should have it as a nice reference as you do your lab. Good luck with everything.
Thank you.
I actually had one more question. I'm so sorry.
Oh, no worries. We have 17 seconds though. So if you get cut off, just log back in.
It's just the, where to go? Oh God.
Don't worry, just log back in. It's going to cut you off.
Okay.
I will restart the meeting.
Okay. Actually, no,